Okay, in this episode, unfortunately, we ran into a little problem with the Hike Micro, the first defect that we ran into, which turns out to be that the HDMI didn't work to the large TV we were going to use for showing how leak detection works, so you could watch the entire operation. So we'll return to that once we have that repaired. We'll reach out. We're going to need to use it for it's getting used. Originally, I got it for one project. It's going to be solidly used over the next 3 weeks on other projects. Then we should, I believe, probably get a break in there so we can send it in for fixing. In any case, so we'll return to that at another time. What we're going to do today instead is I'm going to do, because it's been a long time since I've done an overview of the EMPATH software. We're going to do a complete tour of the latest version of the software. We're not going to collect data on this one. We'll do that next week. I'm going to show you analyzing a set of data. Now, this is data that we used for the energy study. This was done on a dynamometer. This, I believe, is the 50 horsepower motor. So we know there's some misalignment, and we especially know there's some resonance. So I'm going to show you, and I'll be able to show you an interesting aspect of the energy portion of the, unbalance and misalignment. Basically, to summarize that, is resonance doesn't transfer into motor energy use. It is energy loss, but it's loss from resonance going into the facility. Now, some people think, oh, that's magic new energy. Not really. The minute you try to utilize that, you dampen it and it goes away. So let's take a look at a machine. So first, let's take a look at some of the new stuff over before. So let's take a look at setup options, where this first part here is the serial number for your unit. We've got a lot of these out there because this unit is a number of months old and you can see the serial number. In any case, so acquisition, I always turn this off, but the FFT block, in order to get our level of resolution, we set that nice and basically 65/536 FFT block, depending on the amount of time I get, gives me a really tight resolution. I leave this off, so everything else I usually leave in. This one here, again, making sure it's 65/536. I can change the number of averages. However, unlike vibration, which usually uses 2 averages, we use 3 averages in ESA normally. Well, at least we do. This one here is the common settings for everything. Don't know why that turned off, but this allows me to look for electrical issues in the winding. And I use this, it's a stator electrical fault. Now, this is a different type of reading versus interturn short, which the software, we still call it interturn short. In reality, it is winding stress, partial discharge, sparking in the slot. Improperly set variable frequency drives will show this, and sometimes stator electrical fault. If I'm going out and I'm doing straight data collection and I'm not doing continuous monitoring, I will go ahead and click on the unidentified peaks prompt. What that does is it looks for basically any non-integer multiple of running speed and calls it out as a possible bearing. So if I don't have my bearing information, I can select that. DC value, I leave that there. I can extend the high frequency download length to get even better resolution. Right now it does about 9 seconds. If I go to 46 seconds, that'll give me about 1.5 minutes to collect data. Personally, I like the 48 seconds. So 48 seconds to rule the world is how I usually put it. Here, this is new to the software. This would be my kilowatt hour cost, or kWh cost, in dollars, or whatever I want. So in this case, this is 10 cents per kilowatt hour. And then here, carbon emissions cost. This is the present national average for if you correct for something. So if I'm doing an inventory, it's going to be a different value. Most of them fall under 0.5. And this is basically in tons, metric tons, which is 2,240 pounds per megawatt hour. Okay, so 0.699 is the national average published this year. Used to be 0.709 if you look at some of my other articles, and 0.707 depending on who you talk to. The new one is this, and this is for avoidance. So if I go in and I have losses associated with a bearing or something like that, and I correct it, I use this. It's referred to as the AVERT method. This is the proper method per the U.S. Department of Energy. I'll cover later. I'll cover the ISO 51000, but right now we'll say we'll use this. Now, if I'm doing an inventory, like for this area, it'd be 0.498 metric tons per megawatt hour. So that's that. EMP2, that's the next one. Just this is different capabilities. I definitely want the extras tab. That gives me everything, including energy calculations and so on. This allows me to change different colors for the different channels. Channel 1, 3, and 5 is current. Channel 2, 4, and 6 is voltage. Channel 7 and 8 normally are pass-through channels. However, for the system that I have, we had the vibration analysis capability built in, so those are actually vibration for me. Channel 11 is a converted number from using voltage and current, and they derive data from that, and that's in kilowatts. And then finally, this one here. And this allows me to alter some of my alarms. Now, things that we also included. So current deviation of 5%. I just set it at 10%. There is no standard for current deviation. No matter who tells you what, it doesn't exist. So here, this. So let's start from the top. Detection amplitude. Anything that falls as a lower number than minus 85, so minus 90, for instance, a lower number, will not be detected. I set my unbalance tight, so at about minus 60 dB, that's the default now. If I have one-time RPM peaks that show up there, it's unbalanced or misalignment. DC motor flag amplitude, so any peaks that fall higher, so closer to 0 than minus 30 are flagged. Power factor, I set it at 75 to get rid of the constant red that shows up, but for fun, we'll just set it at 85. Actually, we're not going to see anything on this motor because I believe it's about 0.9. Minimum load to make a rotor bar call. It's set at 25% as default, primarily because if I have varying loads and so on, my pole pass frequency might sink in to my line frequency peak. I set it down to the lowest possible value, which is 5%, which means coupled and unloaded. Voltage deviation, that you can set up 5% is the maximum deviation. And then the other ones, belt harmonic and second harmonic of the belt frequencies will give you certain things. Belt slip allowing up to 3%. I can set that tighter if I want. 3% tends to be the average for an 80 to 85% efficient belt. If I'm dealing with a notched belt, not a timing belt, but a notch belt and so on, I might go to 1 to 2%, which is the efficiency. Gear mesh, and hunting tooth, those values have to exceed minus 55, so they have to be closer to 0. I can change that. And then blade pass noise, that's a higher frequency set of, almost like a cavitation. And then here's my harmonic limits for current and voltage. I do leave these as percentages of the total. And you can make these tighter if you want. They're all based on standards. Now there is one more, and this is for continuous monitoring. If I come in here, this is where I set to say that I'm using accelerometers. Kind of surprised that's not set. And then these are other things that I would use for continuous monitoring. But those two should have been set. That's right, I updated the software without doing anything. So let's go ahead and we'll get out of here. And let's take a look at, and if I am doing continuous monitoring, the nuclear button, that is something that turns on and off continuous monitoring. That will be another demonstration. Probably, let's see, next week I'll do data collection, and 2 weeks after I'll do that. And then sometime after that I'll have the Hike Micro back. This is manipulating stuff, and this allows me to select whether I'm looking at the high frequency or low frequency data. This is the default. So if I'm going in and I'm going to collect data, what I like to do ahead of time, and it's usually a good idea, is get my nameplate data in. Finish filling out, and I can pull it over from the other screen. So this was an induction motor. I didn't put anything in for the driven equipment, but I have options. There's some other stuff I can do here too. We'll get into that in a second. What type of data I'm going to collect. Just leave this as default here. Somebody was trying to convince somebody that power factor varies based on that. I generally don't click on any of these because they affect the findings. Basically, this is set up to allow me to have false positives. And for me, that's important. I want to get false positives so that I can look at the data myself and agree or disagree. So I leave a lot of stuff out. So I don't know, if I don't know the rotor bars, I might select this. If I don't know certain other things, I might select it. I leave wound rotor motor out. That was put in at some time in the past because there was somebody who didn't agree with the pole pass frequency signatures on a wound rotor motor, but they're absolutely essential. So pole pass frequencies in a wound rotor motor are going to indicate a problem with the slip ring. If it's got resistors in the circuit, it might be because of unbalances or connections there. Could also be the brush and slip rings. So whoop-de-doo. Don't check it. Reciprocating equipment will not allow you to see one-time RPM. I say heck with that if it's properly done, and I'll be able to show you a reciprocating compressor at another time where they size the flywheel correctly so you don't even notice. None of the stuff passes back, which means that's going to protect the rotor bars. I am going to leave in here 24 hours per day. You would want to adjust that so that you come out to how many ever hours are total for the machine, because this is part of that calculation for losses. And I'll show you, because right now I have these set up for 8760, which is a full year, 24/7 basically. And then I have my motor information in. I can put an efficiency value down. I leave a -1 in. If I don't know what the nameplate efficiency is, it will go off of the default of whatever I select here. So let's go ahead. We're going to call it a premium efficient motor, even though it's not. It's just an energy efficient motor. But we're going to do that for a reason. And then all this stuff here has to do with continuous monitoring. I'm not worried about that because I'm doing data collection. Next thing is in test info. I can put this stuff in. Don't change the top ones. These here, if I want to. The database here, that goes back to this key and everything else. It's an access database. I can do all kinds of stuff with that. That'll be something we'll cover another time. Manufacturer. Now, one of the things I can do here is I can get a drop down of what are called, well, they're special user files. They're .usr files or text. I can put together an entire powertrain. So for instance, these are, well, not the Model T, obviously. That was kind of funny. In the pump test, that's a special pump. But the other ones are set up for wind turbine type gearbox systems. So let's get rid of that because I don't want to have that in there. But if I have that there, it's going to pop up information here, including all of the bearings and all of the components that I set up. So I can do that separately. We're going to release a software that automatically generates those. Let's see, bearing information. Whoops. That's the software trying to catch up. Sorry. Computer's complaining. There we go. That's my computer because I'm running this system in the background, and I've got a couple other background things that are running that take up a lot of memory. So pardon me. But here's the database thing, just to give you an idea. It's gonna, please wait while it pulls up the database of 68,000 and whatever, so almost 69,000 bearings of all types and sizes. And in those, it'll have the inner race, outer race, cage frequency, and ball spin. Now, this is just for the motor, so I'd set up a USR file for all of my other systems. Okay. And I'm going to have to pause to let this thing. Yep, just like I thought. So in here, pretty much a majority of your bearing manufacturers are in here, and I can select all that data. This is just for continuous monitoring, and it's all meant to help you determine whether you're going to collect things or turn off certain alarms. Again, more information, any comments you want to have, like this is what's showing up out here, but I can do that also later in individual reports. So coming back here, I put all this information in. The other thing I get to do is, especially when I get down here, rotor bars and stator slots, is our good old-fashioned rotor bar and stator slot database. And there's I think over 9,000 motors of most manufacturers in here. I can go through and say, okay, say it's a, just for fun, we'll call it Baldor. Let's say 50 horsepower. Oh, we're looking at GE, aren't we? So let's actually, we'll go ahead and change that to a GE 50 horsepower. I'm not going to put anything else in. We hit enter. You can see the background changes. So then I can go over here and say, look for the frame size. I always do that. I look for the frame size. So horsepower, RPM, let's say this is an 1800 RPM. So there's my 1800 RPMs. And I look at the frame size as well. And you'll notice something here is when I get into the same frame size and everything, let's say 48 and 38. When I get up to jump up to 35, 60 or 2-pole, you know, some of those might change. But in general, most manufacturers like to stay with the same size. So 460 volt, 1780 RPM, 326 T frame is generally going to be 38 and 48. Why did I select 40? Probably because I don't know. So let's go ahead and we're going to change this to 38. Well, I'll leave here. I don't usually copy them in. So let's do this for fun. Actually, no. I had confirmed it was 40. So we're going to leave that at 40. Okay, so ignore me. Let's go ahead and continue. So I click OK. That's now done. That's now set this up. So every time I select a data set, I get to populate here. So that's the setup portion. The other part that I want to be concerned about is, I call it sick face. Click on that. And this is going to be all of the settings for what I'm collecting with. So 7 and 8 are selected. That's the picocoulombs per acceleration. So that and this should be about the same. They're both calibrated really close, so I just made them the same. And then here, if I click on, there, let's get rid of these. If I want all 3 phases to show up on the same thing, oops, try it again. There we go. And same thing with 2. All the flickering and everything has to do with the resources I'm taking up on here. So once that's set up, and if I come in here, so the current clamp I'm going to use is 10 millivolt per amp. I won't have the same thing in voltage, 10 millivolt per amp. And you notice this now is at 0. Used to be that there was a 1, 10, 100, 1000 in here. We got rid of that. That's now all automatic. So that's stuff I need for collecting data. Now, if I have the wrong one in, and this happens once in a while, where say I'm using a different kind of clamp, say I'm doing elevators, and I clip on with an elevator clamp that is 1 millivolt per amp, and then the other 2 were left at 10 millivolt per amp, and I go and I collect data, and you notice that the one current is extremely higher than the other ones. There is corrections for that. It's in the user manual, but also we can walk you through it. It's really straightforward, pretty simple. Okay, so let's see if I can get this going. There we go. So let's go ahead and let's open up a machine. So we're going to do this one, which was, is this our vertical readings? So G50, this would be our horizontal readings. Let's see how quickly it opens up. I might have to pause. Yeah, I'll just pause and allow it catch up. Okay, there we go. So it will automatically try to find the spot. So you can see I've got a high one time. This is my demodulated spectrum. So depending on what I want to do, I can turn on quite a bit. Oh, 10 is nothing, sorry. There's 9. I can turn on, so this will be one phase. The higher frequency will do multiple phases. And this data was taken over a period of time. And I'll just pause in between whenever I'm doing this. There we go, that didn't take long. There's my peak-to-peak voltage and current. I'm going to open up 2 more here. Oh no, that should be everything. Oh no, that's vibration, sorry. That's my my vibration data. Let's go ahead and we'll open these up too. That'd be demod. You can see I can open up a lot of data. I can, have these overlaid. I can do other things just by doing that click and drag like I did on the other ones. Let me pause again. There we go. Main reason I wanted to do that is just so I could get the RMS stuff up. So this is my peak-to-peak voltage, peak-to-peak current. So voltage and current, sorry. Voltage on the bottom. This is the 2-channel straight through. This is the vibration data. Also over here, vibration data. This is my RMS current. So that was what was supposed to show up in the other ones. So there and there. So that's my demod. And then this is my current spectrum. So this is mostly what we will work with. So what I can do now is just get rid of those, and now I'll end up with 4, and that'll be vibration and my ESA. So voltage and current, and both channels. Now really Do I need to worry about voltage? Yeah, sometimes. I'll notice here too that this noise floor is really low. So we're going to do one more thing here. And I am going to go to Layout, FFT type, and normalize based on. Oh, I'm going to have to do that in high frequency, aren't I? Okay, so we'll go back to that. That's a new feature. So anyways, you can see here's my running speed RPM. This is important. I can take a look at something and say I have minus 66 and minus 64 dB on this one-time RPM. Zoom in, take a close look. You see my peaks here. I got peaks here. Whichever peak is higher, so minus 68 and minus 64, that's going to be some level of unbalance, maybe? Yeah, so, yep. So this one's a little higher than this one's a little higher than this one. That creates a bit of confusion, so it's probably going to be that, but let's figure it out. But because that's higher on one versus the other, and it's right there at 1787.5, so it's not exactly the zero. That's my actual whatever. So let's go ahead and we're going to kick open the calculator. The calculator is cool because what the calculator does, and I'm going to have to pause again, is it runs the analysis for me. It'll tell me exactly what it sees. So we'll return to this in a minute. Notice the rotor says C2. That's because I have pole pass frequencies. I have one there and I have one there. It should be going off of this one here, which is at minus 50, which would be C2. I don't start worrying about it too much till later on. It's also important to understand because an awful lot of people will condemn a motor. This is a 460 volt motor. It's 50 horsepower. It's small. It's got cast aluminum rotor. A lot of people will condemn pole pass frequencies on a cast aluminum rotor, even cast copper, and say it's a defect. I'm sorry, every single rotor that has a cast rotor looks like Swiss cheese if you cut it up. No matter what the copper industry says, too. So both aluminum and copper end up with voids. You can tell where the largest number of them are by where the balancing weight goes on the rotor, by the way. So I have this, and this is vibration data. This raised floor here, the dynamometer we're using is water-cooled. That is cavitation. That's water flow. Okay, I can see the same thing with turbulence in fans. So if I see a raised noise floor like this, I know it's some kind of cavitation or turbulence or something along those lines. So we take a look. We have this here. Let's do our quick tour of this, and then we're going to look at the high frequency data set. Again, you notice this is the vibration spectrum here. So results, it takes a look there. Here's something where it flagged it. Here's the time. So my power factor is 0.94. Total kilowatts, this is important, input kilowatts. Shaft kilowatts are down here. So input kilowatts, 31.8. Output is 27.8. So let me mark something down here. I knew these notes would be good for something. We're going to say, okay, so that is input 31.8, output 27.8. That gives me about 4 kilowatts loss. Okay, in order to obtain that load and the 92.5% efficiency, you'll also notice it determines the output torque. So I have that, there's my current, there's my voltage, and I might have, in this case, I have 85% of load. even though the current might not match the load, current will often be up between 5 and 10% off the actual load. Frequency, and there's another thing you'll notice there, is my current and voltage total harmonic distortion. Bearings, which are all saying okay. Here's something I can do, by the way. If I'm in here, let's go ahead and zoom back. There we go. If I want to see where the peaks are, I double click on it, and there's my peak for inner race coil, or a cage, ball spin and outer race. And I can troubleshoot it myself. It basically does the calculations for me. The right running speed times the different multipliers, and I'll show those peaks and do them as sidebands, as it should. Time, again, we just looked at that. Frequency, that's going to be that information. Bearings, that's what we just looked at. Phasers, it's going to show me either in actual values, and I can change this, I think, up to 51. Is it going to let 51, or it's either going to be that or 50? Yep, 50. And I can convert this over to a percentage, or I can look at harmonics table. There we go. So I have those, and then finally the extras button, which is really kind of cool. So this is all the values it's using for making its decision. This is certain other things. So it says, oh, we got minus 68 for static eccentricity, and then finally, it's one where it says losses. There's a lot of harmonic content in this one that go along with that harmonic. That of the 4 kilowatts between the incoming power and outgoing power makes up 1 kilowatt of that loss. So that means the harmonics are 1% of my 31.8. And that would be, because 31.8 is what I would be reading if I was doing an energy monitoring. So 1 divided by 31.8 is about 3% losses associated with harmonics. Bearing losses, it just determined they were good, so it didn't flag anything. Unbalanced, that high one time, is 13.6 watts, 11.9. So, and this, by the way, is based on the full year. This is the metric tons of CO2 per year. So it'll do that, and then it's going to total everything up. So all my losses between the incoming power and the shaft come out to be about just over 2 kilowatts, so about half. This one here, hold on just 1 second. Sorry, I had to take care of something. And then, so anyways, so then it calculates all that stuff. The last version, this is the one that's about to be released. So nobody else has this yet other than me and the software programmers. These are the corrected values from that. So the last one was a little high. This is conservative again, and I'll show you what those numbers come out as, especially the one here where it says 13.6. Remember 13.6. I'm going to write that down, 13.6. Okay, so that's watts, not kilowatts, watts. So that all adds up, of course. So this here is one, and then it comes up with a total cost for me per year. So my cost for all of those losses comes out to be about $1,800 plus 12 tons of CO2 per year. So that's that. The other thing is this guy right here, torque. This is my air gap torque. Okay, so it'll show that. It'll show those peaks, both in my. It's going to give me a little bit of a conniption. Here we go, and you can actually see some of this rolling right there is actually from the casting void. There it goes, and I have that Anywhere where I see print, it'll just print the graphics out for me. And there we go. So I have that. We're going to keep this around because I'm going to use this to show you how to do the easy way. I can also use this here to do all those things that I just did. Waterfall plot's not set up for this right now. Let's see, all the statistics, those pop up as numbers and all the other little stuff that's there. I can change the type of FFT window, Hanning, flat top. See if the waterfall shows up. Oh, there we go. So the waterfall button isn't working, but I can do a waterfall of whatever I highlight. So that's voltage and layout, waterfall. You can see all kinds of shortcuts. So there's what's happening. So if I'm looking and I see a broad noise floor, I can see if it's consistent, which would be looseness, or if I can see if it varies, which would be changes in speed. So once I get through that stuff, let's go ahead and take a look at the high frequency data. Now, because I'm taking my high frequency data at 12 kilohertz, that means that I am seeing out to 6 kilohertz for my Fmax. And I'm down to about 1/100th of a hertz as far as accuracy goes. So that means all my peaks can split up. By the way, that means that when I'm doing my EMPATH data, I can get down to no load uncoupled. There was some suggestions that you needed at least 60 or 70% of load. That's not the EMPATH. That is somebody else's. That's somebody else's system or other systems on the market. We can go all the way down to no load. So you see that my noise floor disappears. So let's go ahead, and this time we're going to change that noise floor. Change minimum dB level. Normally minus 120 will do it. It's going to pop it up. Personally, I like to see the noise floor. In reality, I'm not worrying about peaks under about 65 dB down. So in any case, this gives me the ability to look at what this all looks like and roll off of about right around 5,500. So let's get this back open. There we go. And you can see it says static eccentricity. Well, that is the number of rotor bars times the RPM plus and minus 1, 3, and 5 times the line frequency. So if I double click this, it'll pop this up. I can also get there this way. Okay, so one of the things I want to do is show my power harmonics, which are Christmas, so red and green, and I show those up because if my peaks and everything else line up with that, it could just be harmonic. So a lot of this is harmonic. So let's go ahead and we're going to zoom in close. Okay, a lot of side bands around it. So there's something going on here. Those starts out with these two peaks out here and just follows all the way out. So there's something going on with the piece of equipment and the driven dynamometer, and it's possible it's old. So I have that. If I'm curious, if I want to understand what else is going on, I can double click stuff and it's going to pop up my values for it. Let's say misalignment or imbalance. That'll pop up. Stator fault. Here we go. Poof out here. That would be any type of stator defect. There's a couple of peaks pretty close, but they minus 100, so they actually are falling just on the other side of that. Let's take a closer look. Okay, so right there. But you know what? Let's take a look, because we had added in stator electrical damage. No. So it basically ran out and it did a little bit extra there. And it's well outside that. So nothing really stands out. Winding stress curses, we're going to do that next. Dynamic eccentricity. So let's take a step back. There we go. And let's take a look and see if we have mechanical or magnetic orbit going on. So you can see, poof, there we go. Nope, no peaks associated with those. So we're good there. So in addition to this, I can go through and I can look at a lot of other things. Now let's see if we have any winding stress going on. There we go. So winding stress would be, those are the conditions where, if we're on a VFD or something along those lines. Now these peaks that line up exactly, you see it's shifted a little bit and just off peak. I'm not going to pay too much attention to that, but some of those other peaks that were standing out, those are showing up a bit too. So, and they're not in voltage. So winding stress would be something going on with the winding. It's possible. So in this case, I would just state that a possibility. I might do some other testing just to verify it. This is not on a VFD, but it's on a control that had recently, well, just say it's been recently repaired. But there's also other things going on with the motor. So you can see that I have peaks and then I have resonance of it and so on. And let's see, did we cover everything on here? Sure. And then the bearings, I think, were identical. They are. So there shouldn't be any changes with that. You can see I'll get one set of whatever up at a time. And yeah, so they don't line up with anything significant. Now, let's do the next bit. What I want to do is look at the vibration data, and let's take a look at the kilowatts. Or the watts. So we're going to open these up. And the first thing it's going to do, by default, it's going to open them up as dB. So nasty looking. What can I do with that? Nothing. So I don't care. What I am going to do is go to Layout, FFT type, and go to Linear. And before I do that, you'll see that this guy right there, it says Create ASCII file. I can take all this data and export it as a CSV and have fun with it. So let's go ahead though, and we are going to change this to FFT type linear. That means I'm going to be converted over to, and let's make sure that these are actually going to be in inches per second, because it collects it normally in dB, but just to verify, yeah, there it is. Velocity. So that will be inches per second. Here's all my kilowatts and everything else. You can see all the peaks are quite low. And this would be everything associated with the defects. Okay, so I can calculate them out. I can even relate, and this is the study we're doing for next month. Actually, I'll be presenting it a week ago next month. They do have me set up to present on Thursday. So here we go. Oh, and it's pulled up anything that might be bearing related. So I can actually look at my, vibration and any losses. Down here you can see there's a small peak at pole pass frequency, which that's about 37 watts or 0.037 kilowatts. But let's take a look and see, because if you remember right, we were at 13.6 watts for unbalanced calculated, and that is telling me about 19 watts. So close enough for it to work. Yeah, close enough. Actually, it was a little conservative. And that's because what we did is it's reading off of the spectra, but it's doing a plus or minus, I think half a hertz or something like that. So a little bit of the side part is gone. Yeah, so you see that plus or minus a half, so 29.8. That would be, yeah, 30.3, so right about here. So this bit wasn't included and this bit wasn't included. So not worrying about that, because that means that I'm using a conservative value, and that's really what I want to do, because if I go in and say, hey, boss, we're using 5 kilowatts of energy in this motor due to all these defects, and you fix them, and you come back and say, well, it was actually 8. That's a win. That's not a loss. That's an improvement and everything else. But in this case, because the base is loose on that application, that's 0.66 inches per second, and up here we're at 0.25 roughly inches per second, and those do relate, and that's what we're presenting. There's a curve that relates to. So with that, we pretty much covered a majority of the system. I made it as complicated as I possibly could. It's a full tour of all the capabilities. In reality, let's take a look at what I end up doing. So if I come in here, I might grab a machine like this. I'll grab the other set of data. I open it up. If I'm doing an analysis, and there we go. It's showing me data. Obviously, one-time RPM, not quite good, and I'm at about minus 50. So I know I have casting voids or broken rotor bars. So next thing I'm going to want to do is open this up to see, because those are potentially serious conditions. This could be unbalance related to that, and then I might continue working along. So here we go. It says I've got static eccentricity and I have a one-time RPM. That's misalignment with soft foot. Why? Because static eccentricity, and it twists a little bit if I tighten down the bolts. There you go. So with the rotor shifted off center, that's static eccentricity. Now what I want to do then is say, okay, I'm seeing this. I could probably set my alarms tighter. I'm at about, like I said, minus 64 and minus 64. So it didn't hit 65, so it didn't call it. I'm sorry, 60, right? Yeah, so it's greater than 60, so it's not lower than 60, so it didn't call it. Now, if I had put that in, let's change it. And we're going to say unbalance at minus 50, minus 70. So we're going to really lower it down. This is going to call everything. Give me false positives and everything else. There we go. Now it's calling a misalignment or unbalance. Okay, but at that level, really, the misalignment or unbalance is not going to be as significant as the actual value we're receiving because of the resonance. Now, by doing the combination of those, I can start seeing what's going on with the machine and know what it is. So, I know that I'm going to want to run out and do a motion amplification. This is my horizontal. So, which would look like, because I did do it. Let's see what happens if I'm able to open it up. One of these. It's the 50 horsepower. That's from the side. Let's go from the back. So what this looks like in motion amplification, we're going to pull that up here in just a second. So I know I have soft foot. I know I have 1-time RPM. Now it's very, very low, of course. And let me pause. Okay, so here we go. This is the back of it. This is the dynamometer that it's on. There's my amplitudes. That's about right. The highest one was in the x-axis, but let's go ahead and play this, and you can actually see the movement side to side, right? So that is primarily going to be a resonance, but it's not that value. As you can see, it's not moving a lot vertically. It's moving primarily horizontally, which means in the air gap, it's doing certain things. And when I add the vertical and the horizontal, then I can get a value that relates. So that's that. Now, one of the things you'll note is that I'm not going to see in motion amplification things like rotor bar frequencies and the like. But with that, if you have any questions on the EMPATH system or software, reach out to me. The email address will follow up, or one of my staff. The email address will follow up immediately after at info@motordoc.com. I try to answer most email communications from customers and potential customers, but there's people complaining and want to do some of it too, so we'll probably change. In any case, with that, it's getting sunny out, so it's almost time for my walk. So have a good day, and we will see you next week.